All right, let's take a look at 2012 problem 6. It says the function g has derivatives of all orders, and the Maclaurin series for g is given by the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 3, and then they've got it expanded term by term as well. You'll see for this problem that sometimes we prefer the sigma notation, and then there are times when we'll prefer the expanded out version. If by chance they were only to give you the sigma notation, I hope everybody knows you can just start plugging in 0, then 1, then 2, and so on, and then you can do your own expanded out version. Or if they only give you the expanded out version, you could always figure out the pattern and then make up your own sigma version. So let's go ahead and look at part A. It says, using the ratio test, determine the interval of convergence of the Maclaurin series for G. Now, a quick comment on why we're going to use the ratio test. Number one, because they told us to, but number two, because unfortunately this is not geometric, you can tell, because they don't keep multiplying by the same thing every time to generate new terms. I'm only mentioning that because if you get so lucky as to be given something that is geometric, remember you just take the common ratio and you bound it between -1 and 1. You would not need to check endpoints or anything, but here we are using ratio test, in which case we'll need to do the checking endpoints and all that. So let's go through it. Part A, when it says, so I'll just kind of start with my little prompt. We enforce. It's a good little thing to have for the times when they say you need to explain the condition of convergence of the ratio test. Okay, so we're going to take the limit as n approaches infinity of, now I'm going to write this, but I'm going to erase it. Remember, we're going to take a sub n plus 1 divided by a sub n, where this right here is the rule for a sub n for your general nth term, okay? So to get a sub n plus 1, you take all the n's out and you replace them with n plus 1. So -1 to the n becomes -1 to the n plus 1. X to the 2n plus 1 becomes x to the 2 times the quantity n plus 1 plus 1. Which simplifies after you distribute the 2 in and combine like terms, it simplifies to be x to the 2n plus 3. Similarly, replace n with n plus 1, distribute the 2, and on the bottom you get 2n plus 5. Now, dividing by a sub n is the same as multiplying by its reciprocal, so we're going to multiply by 2n plus 3 over -1 to the n times x to the 2n plus 1. And then since we are enforcing the condition of convergence, that means that we're going to force this to be less than 1. Now all we have to do is solve for the x values that make this inequality be true, and then we'll know our interval of convergence. So let's simplify things just a little bit. So canceling, so the -1 to the n and -1 to the n plus 1, all of these guys cancel out all but one of these guys. The x to the 2n plus 1 and x to the 2n plus 3, these guys would cancel out all but two of these guys. Remember the idea of subtracting the exponents when you're dividing. Really, it was just a matter of figuring out how many don't cancel out. And then the 2n plus 3 and the 2n plus 5, I'm just going to leave the way they are. So what do I now have? I have the limit as n goes to infinity of the absolute value of -1 times x squared. And I'm going to group the n stuff all together. So I'm just going to write it like this. 2n plus 3 over 2n plus 5. And we're looking for this to be less than 1. So now let's talk about, as far as the limit is concerned, the n is the variable. So as far as the limit is concerned, things in terms of x are constants. So that means that you could factor this stuff out. Keep in mind it would still need to be in absolute value marks. And because it's an absolute value marks, the -1 ends up being redundant or unnecessary because the absolute value of something negative is positive anyway. So I'm just going to write it as the absolute value of x squared for all of this being kind of pulled out in front of the limit, and then times the limit as n approaches infinity of 2n plus 3 over 2n plus 5. And we're looking for this to be less than 1. Okay, now let's evaluate this limit. I hope you agree that value would be 1. Remember, oops, if you write the right thing. Okay, you could use horizontal asymptote rules from way back in Algebra 2 if you want, but the value of that would be 1. So we would be left with looking for the absolute value of x squared to be less than 1. Now, up to you how you solve this. You could just number sense it out and figure out that x would need to be between -1 and 1. Or if that makes you feel very uncomfortable, you could look at the graph of y equals x squared, or think about it in your mind's eye. And so here's the graph of y equals x squared, and you're looking for when this would be less than 1. And so it would be less than 1, you could see from the picture, for x values between -1 and 1, not including those values because we didn't say less than or equal to 1, and then everything from there to there. Okay, so at this point, you could say that x would be anything from -1 to 1. And then at this point, we have no reason to include those endpoint values. But because this wasn't geometric, we should check the endpoints. So, because remember, the reason you have to check endpoints is because it's the -1 and 1 that would have made this expression be exactly 1. And then the ratio test was inconclusive for those points, meaning it could have gone either way. For checking endpoints, I really like going back to the sigma notation version. You could always also expand it out if that helps you, but I really like sigma notation for these. So I'm going to check x equaling -1, and we're just going to look at up here, if x is a -1, what kind of sum do we get? So just replace that 1x right there with a -1 and bring everything else down around it. Okay. Up to you what you want to do with this top part. I think I'm going to use a property of exponents. Since the base is the same and you're multiplying, you could just add the exponents. Okay, and then let's think about as n goes from 0 to 1 to 2, what happens with this exponent right here. So if n's 0, you'd have an exponent of 1, in which case you'd have -1 to the 1, which would be -1. If n is 1, you would have 4. So now you'd have -1 to the 4th, which would be a positive 1. If n is 2, you'd have 7. And so hopefully you can see that the value here alternates between positive and negative. And since your exponent is alternating between positive and negative values, you'd end up with something here, up here as your numerator, that alternates between positive and -1. So what that means then is that you have an alternating series. And what's the non-alternating part? The non-alternating part would be 1 over 2n plus 3. Okay, and remember with an alternating series, if you can say the non-alternating part is always positive, the limit as n goes to infinity, that this would go to 0, and if you could say that this decreases in value as n increases, then you could say that the alternating series is convergent. And you wouldn't especially have to list all of that thinking out, but you would need to think it through in your head and come up with a conclusion that this is a convergent alternating series. I do have a strong feeling that alternating series test for convergence is going to be on your test when you take it. So if that has kind of slipped away from you, then I would say go back either in your notes or in the textbook and look that up and maybe practice it a little bit to make sure that you remember that one, okay? X equaling 1, same thing, you guys. You're just going to go back to the original sigma notation, just replace any x values, which there's only this one and this one, and with a positive 1. So you'd have negative 1 to the n times 1 to the 2n plus 1 over 2n plus 3. And then that would be the sum as n goes from 0 to infinity. 1 to all these exponents is just going to be positive 1. So you're just left with negative 1 to the n over 2n plus 3. And here we are. We basically have the exact same situation we had up here. It's a convergent alternating series. Okay, so what does that mean? Since when we put negative 1 in, we got something that converges, it means that you would include negative 1 in your interval of convergence. And since when we put x equaling positive 1 in, we also got something that converges, you would include x equaling positive 1 for something that, as something that converges. So your answer would be, therefore, your interval of convergence is x values from negative 1 to positive 1, including both endpoints in this case. All right, my friends, I hope that helps. Okay, let's move on to part B. Okay, part B. The Maclaurin series for G evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. The approximation, so decrease in absolute value to 0. My friends, they're saying that it converges. That's what that's saying. That's a convergent alternating series, but we have other ways to figure that out. The approximation for G of 1/2 using the first two non-zero terms of this series is 17 over 120. Show that this approximation differs from the true evaluation at 1/2 by less than 1/200th. So we're going to use the convergent alternating series remainder theorem. You have a flashcard for this. It would be a very good idea to review it if you are feeling rusty on it. So what I'm going to do here, I like the term by term side for this problem. So since they said that they're just using the first two terms to do the approximation, just having the first three terms is going to work great for this problem. So I'm going to copy like that, okay? And then we're going to do, well, let's look at what G of 1/2 would be. So it'd just be 1/2 in for all the x's. Okay. Now, we know that this is a convergent alternating series for quite a few reasons. One, they pretty much said so. Terms decrease in absolute value to 0. That is pretty much, that is what it takes for an alternating series to converge. And since it's a convergent alternating series, we can use the convergent alternating series remainder theorem. So a couple things. They said, and that bless their hearts, because it saves me a little time. They said, hey, look, if you combine those two together, you're going to get 17 over 120, okay? Another reason for us to know that this is a convergent alternating series is because you're plugging 1/2 in, and in the previous problem, in part A, we found that that series will converge for anything between -1 and 1, which 1/2 lives there, so there you go. So I'm just going to go ahead and say, since G of 1/2 is represented by a convergent alternating series, the difference between the value of the infinite sum, meaning if you did include all the infinitely many terms that it takes, and in this case, the second partial sum is going to be less than the, you could say absolute value or magnitude. I like magnitude because it's shorter, of the, do you remember? First neglected term. Now, I'm going to say exactly that, but in math speak. And I really feel like it's the math speak that serves me really well in this situation. That is the absolute value of f of 2 take away, and I'm just going to call it 17 over 120. That is what they said your first two terms would add up to, is guaranteed to be less than the absolute value of your first neglected term. So I'm going to put 1/2 to the 5th over 7 in there. It's already positive, so the absolute value marks aren't doing much. So let's figure out what this value is. 1/2 to the 5th is 1 over 32. And we're going to have to do 32 times 7, which is 210 plus 14, which is, I think, 224. And that, my friends, is less than 1/200. So what do we have? So this is less than this number, and this number in turn is less than this number. And so we have this is less than 1 over 200. There we go. And that's what they wanted for that. Okay? You would not have to rewrite this. This kind of run on equality and inequality statement would totally do it for you. All right, my friends. Okay, let's move on to part C. It says, write the first 3 non-zero terms and the general term of the Maclaurin series for g prime of x. So I'm going to copy down what they said g of x was. So g of x, they gave us the first 3 terms of g of x. And then they also gave us the general term for g of x. Like so. So let's just take the derivative of both sides. So g prime of x would be d dx of x over 3 is just 1/3 minus derivative x cubed over 5 would be 3/5 x squared plus derivative x to the 5th over 7 would be 5/7 x to the 4th, which I guess the next thing would be negative. Now let's talk about the derivative of this term. We're taking the derivative with respect to x, which means that anything in terms of n would be considered a constant as far as our derivative is concerned. So what you get, so I'll make a note here. You're taking d dx of that general term. Just want to make sure that we're kind of seeing how simple this will be, okay? So you're taking, so -1 to the n and 2n plus 3, those are constant multiples as far as this derivative is concerned. So you could factor it out and then just take the derivative of the factor that has the, that's in terms of x. And then this would just be power rule. So you'd have so then 2n plus 1 take away 1 is 2n. Okay, so this is what you're going to see me put up here in for the general term. So I'd have -1 to the n times 2n plus 1 times x to the 2n over 2n plus 3. And then don't forget about the plus dot dot dot, since we're saying g of x is exactly equal to that. And then you've got it. All right, my friends, I hope this helps. And I hope if it doesn't, that you could contact me and let me know what questions you still have. Take care, everybody.